Hello there, and welcome to The Ancient Historian, where curiosity gets cozy and science takes the scenic route to slumber. Tonight, we begin a journey not forward, but outward and inward, into the deep mysteries of the universe. Our focus is a realm long beyond our everyday experience, far beyond Earth, stars, or galaxies as we know them. A place where the rules of space and time bend, twist, and sometimes seem to vanish. We are stepping into the enigmatic heart of a black hole. Black holes are regions in space where gravity reigns supreme, warping everything around them. Light itself cannot escape their grasp, which is why they are called black holes. These cosmic enigmas have fascinated scientists, philosophers, and dreamers alike for decades. They are not merely objects floating in space. They are powerful laboratories of physics, testing the boundaries of everything we know about the universe. Imagine looking at the night sky and realizing that, somewhere out there, massive stars have collapsed under their own weight, forming singularities, points so dense that a teaspoon of their matter would weigh billions of tons. Around these singularities, space stretches and compresses, creating what physicists call the event horizon, the point of no return. Cross it, and everything, matter, light, time itself, falls inward, disappearing from the universe we observe. If this kind of quiet, wandering question stirs your curiosity, I'd love to hear from you. Drop a comment below and share where you're watching from, and what time it is there right now. It's incredible to imagine people all over the world, each following this journey through time together, like scattered sparks tracing the edges of history. If you feel drawn in, tap like or subscribe. It helps this little signal ripple outward, reaching other curious souls moving through the world like shadows chasing sunlight. No pressure. Think of it as a soft invitation, like a drifting feather settling on a hidden path, or the faintest whisper of a story carried on the wind, guiding us somewhere strange, secret, and entirely unexpected. So settle back, let your mind wander, and follow this thread wherever it leads. Tonight, we will explore questions that challenge not just our understanding of the cosmos, but the very laws of reality. What lies inside a black hole? What happens to time, to space, to the matter and energy that vanish into it? Can anything escape? And what do these celestial mysteries reveal about the universe itself? Over the next hours, we'll venture into the shadows where gravity rules unchecked, where stars collapse into infinitesimal points, and where the known and the unknown meet. We'll touch on Einstein's theories, the work of modern astrophysicists, and the mind-bending paradoxes that make black holes one of the greatest enigmas of our cosmos. Prepare yourself to drift past the edge of the familiar, past the spinning galaxies and shining stars into the dark, infinite stretch of space where black holes dwell, quiet, invisible, and yet immensely powerful. Every ripple of gravity, every photon swallowed, every thought we can muster about what occurs beyond the event horizon is part of this story. From here, we begin to peel back the layers, imagining the crushing densities, the impossible forces, the strange geometries of space and time inside these cosmic vacuum cleaners. We will travel in thought and imagination to a place no human has ever visited and attempt to understand the impossible. To understand what lies inside a black hole, we first have to witness how it comes into existence. Imagine a star, far larger than our sun, burning brightly for millions of years, a beacon in the cosmic dark. Inside, nuclear fusion fuses hydrogen into helium, releasing unimaginable energy, holding the star against the relentless pull of its own gravity. This balance, delicate yet enduring, maintains a stellar life for eons. But eventually, the star's fuel begins to dwindle. Hydrogen runs out, and helium fusion takes over, forming heavier elements, one by one. Carbon, oxygen, silicon, all the way up to iron, the final product of fusion. Iron cannot release energy by fusing, and the star loses its ability to resist gravity. For a massive star, this imbalance is catastrophic. Its outer layers collapse inward in a fraction of a second, producing a supernova. An explosion so powerful it can outshine entire galaxies for a brief moment. The core, however, continues to compress. For stars above a certain mass threshold, nothing can stop the collapse. Electrons are forced into atomic nuclei. Protons and neutrons collide, and the core condenses into an infinitesimal point with mass packed into an impossibly small volume. A singularity. Around it, the event horizon forms, a boundary beyond which nothing, not even light, can escape. This marks the birth of a black hole. During this collapse, the laws of physics as we know them begin to falter. Time stretches and slows near the event horizon. Space itself curves, spiraling toward the singularity. Anything caught in this gravitational grip is inexorably drawn inward. Matter is compressed beyond comprehension. Energy transforms, and the very fabric of reality is stretched to extremes. The process is not silent. Supernova send shockwaves across space, scattering elements forged in the stellar heart into the cosmos. These materials seed future stars, planets, and even life itself. In a way, the creation of a black hole is not just an ending. It is a transformation of matter, energy, and space. A dramatic reshaping of the universe at both local and cosmic scales. Even the formation of smaller black holes from stars like our sun's mass presents profound mysteries. If the star is too small, it might form a neutron star instead, a dense remnant packed with neutrons, spinning rapidly and emitting beams of radiation. But for the most massive stars, the collapse is inevitable. The core shrinks, space curves infinitely, and we are left with a black hole. A region where the known rules falter and imagination must take over to understand what exists inside. Gravity near the forming black hole becomes unimaginably strong. Objects caught in the vicinity are stretched and distorted in a process called spaghettification, where tidal forces elongate matter as it plunges inward. Even light bends in this intense gravitational field, creating a sphere of darkness that swallows everything around it. This is where the singularity waits, hidden behind the event horizon. A mysterious point with zero volume and infinite density, at least according to classical physics. Modern astrophysics, including Einstein's general relativity, predicts the behavior of matter and space-time around the singularity, but the singularity itself remains a place where equations break down. Scientists continue to debate what happens beyond the horizon. Does matter truly collapse to a point, or is it transformed into an unknown state? Quantum mechanics hints at possibilities, like black hole evaporation through Hawking radiation, but the interior remains entirely beyond direct observation. The creation of a black hole is both violent and elegant. It is the ultimate demonstration of gravity's power, a cosmic crucible where mass, space, and time converge to create an entity that challenges comprehension. Understanding the formation is the first step toward imagining the interior, toward pondering the extreme, surreal, an unfathomable environment inside these cosmic enigmas. Once a black hole has formed, the most mysterious boundary in the universe comes into play: the event horizon. Picture this invisible sphere surrounding the singularity, a point in space beyond which nothing can escape. Light, the fastest thing in the universe, approaches this boundary only to be trapped, bending, twisting, and ultimately vanishing from the observable cosmos. Crossing the event horizon is a one-way journey, a step into a realm where space and time begin to merge and defy everyday understanding. As you approach, gravity grows unimaginably intense. It is no longer a gentle pull like Earth's gravity. It is a force that stretches, warps, and distorts everything in its path. Any object falling toward the black hole experiences extreme tidal forces. Imagine being pulled into a cosmic blender, stretched lengthwise, compressed widthwise, in a process astrophysicists call spaghettification. Even if you were a massive spacecraft, the difference in gravitational pull between the nearest and farthest ends would tear it apart. Time itself behaves differently. For an observer far from the black hole, time for the falling object appears to slow dramatically. From your own perspective, time feels normal. But to the outside world, you seem frozen at the edge of the horizon. This time dilation is a consequence of general relativity, and it is one of the most mind-bending features of black holes. The closer you get to the singularity, the more extreme the effects. Seconds stretch into hours, minutes into millennia, and space curves until it folds back on itself. Inside the event horizon, the familiar notions of up and down lose all meaning. Space and time are intertwined, a warped continuum that funnels everything toward the singularity. The equations of general relativity suggest that all paths lead inward. There is no turning back, no escape. All matter, energy, and even information that crosses this boundary is inevitably drawn to the core, where density grows without limit and known physics breaks down. Matter falling in is crushed to unimaginable density. Stars, planets, gas clouds, even light itself are compacted into a volume so small that its dimensions approach zero, yet its mass remains enormous. Here, gravity dominates all other forces. The known universe as we experience it, planets orbiting stars, air and water interacting, even atomic structures, ceases to function normally. This is a realm where classical physics meets its limits, and only theoretical physics can attempt to describe what occurs. Magnetic fields, plasma jets, and accretion disks form around the black hole before crossing the horizon, creating some of the universe's most spectacular phenomena. Matter spirals inward, heating to extreme temperatures and emitting powerful X-rays and gamma rays. These signals allow astronomers to study black holes indirectly, offering clues about the immense forces at play and the processes guiding material into the abyss. The interior of a black hole may also hold secrets about the unification of physics. Quantum effects, gravity, and spacetime interact in ways that remain mysterious. Some theories suggest that information swallowed by black holes may not be lost entirely, but encoded on the event horizon, or released over unimaginable timescales through Hawking radiation. These ideas push the boundaries of what we understand about reality itself, challenging scientists to reconcile quantum mechanics with general relativity. Crossing the event horizon is an ultimate journey into the unknown. Inside, space curves to an extreme, matter and energy behave in ways we can barely imagine, and time loses its conventional meaning. The singularity lies at the center, a point where density and gravity become infinite in classical models, a cosmic puzzle that defies observation. Yet, despite the dangers and unknowns, this region fascinates scientists, inspiring theories, debates, and endless curiosity. Gravity, time dilation, spaghettification, and the collapse of matter all converge beyond the event horizon. It is a place where the familiar rules of the universe no longer apply, and imagination must guide understanding. Every moment spent thinking about this space challenges intuition, sparks wonder, and reveals the profound strangeness of our cosmos. Deep inside a black hole lies the singularity, the ultimate unknown, a point where gravity crushes everything into infinite density, and the fabric of space-time curves beyond recognition. Unlike the outer regions, where matter and light spiral and interact, The singularity is a place where the known laws of physics fail. Imagine a single point that contains the mass of an entire star, compressed into a volume so small that dimensions as we understand them vanish. Classical physics says it has zero volume and infinite density, but the truth may be far stranger, something that stretches even the imagination of physicists. Matter approaching the singularity is stretched and compressed in ways that defy intuition. Electrons, protons, and neutrons are squeezed together, atomic structures are obliterated, and particles merge in a state that is not fully understood. Space and time themselves no longer function normally. What does it mean to exist in a region where time might cease to flow as we know it, where all spatial directions lead inward, and where cause and effect as we understand them may lose meaning? Some theories suggest that the singularity could harbor a bridge to another universe or dimension. Wormholes, long speculated in theoretical physics, are often imagined as potential passages connecting distant regions of space-time. While this remains speculative, it illustrates the extreme conditions at the singularity, where the boundary between science and imagination blurs. Every particle, every photon drawn toward the center, is influenced by these incomprehensible forces, creating a cosmic maelstrom of energy and matter. The singularity is also a place where quantum effects may become crucial. Einstein's general relativity predicts infinite density, but quantum mechanics suggests that space and matter are granular at the smallest scales. Reconciling these two frameworks has challenged physicists for decades, leading to ideas like loop quantum gravity or string theory, which attempt to describe a singularity without infinities, replacing them with exotic forms of quantum structure. Time dilation near the singularity is extreme. For anything falling inward, seconds stretch into incomprehensible durations relative to an outside observer. Light trapped near the center bends and spirals, unable to escape, forming a complex web of gravitational interactions. Matter falling in might collide, merge, or even transform into states of energy we have never witnessed, contributing to the dynamic mystery that surrounds the black hole's heart. Visualizing a singularity is almost impossible. Imagine a point so dense that space curves back on itself, a region so small yet containing unimaginable mass. All matter from the surrounding galaxy, compressed and stretched, ultimately converges here. Energy, information, and mass are drawn into this tiny, inscrutable core, creating a cosmic engine unlike anything in the observable universe. Some scientists even propose that the singularity might not be a point but a tiny, spinning ring, a concept known as a Kerr singularity. In this model, rotation prevents a single point of infinite density, creating a loop through which matter could theoretically circulate in bizarre, extreme trajectories. While these ideas remain theoretical, they expand our understanding of the black hole interior, suggesting that even in the most extreme environments, there may be structure and dynamics we are only beginning to grasp. The singularity is the ultimate mystery of a black hole, a place where reality itself seems to warp and distort. Matter, energy, time, and space converge to form something that challenges comprehension. Every calculation, every observation, every theoretical model tries to capture its essence, yet the truth remains hidden behind the event horizon. It is a cosmic puzzle, a place of extremes and the heart of the black hole, quietly bending the universe around it. Inside a black hole, familiar concepts of time and light are twisted beyond recognition. Imagine a place where the ticking of a clock no longer matches reality elsewhere in the universe. As an object approaches the singularity, time slows dramatically for it compared to an outside observer. From a distance, it appears to freeze, suspended at the edge of the event horizon, while for the object itself, time continues in a distorted, unrecognizable flow. Seconds can stretch into years, minutes into millennia. This extreme time dilation is one of the most fascinating aspects of black hole physics, a window into the warping of space-time itself. Light, the fastest traveler in the universe, cannot escape once it crosses the event horizon. Photons, usually unstoppable, spiral inward, bending along the curves of space-time toward the singularity. As they descend, their paths twist, warp, and become trapped in the black hole's intense gravitational grip. The familiar concept of sight loses meaning. If you were inside, nothing from the outside universe could reach you, and nothing you emit could ever return. Darkness dominates, not just as absence of light, but as a fundamental property of the space itself. Information about matter and energy falling in becomes equally complex. According to classical physics, everything crossing the horizon is lost to the outside world. But quantum theory suggests that information cannot be destroyed. This leads to one of the most perplexing debates in modern astrophysics: the black hole information paradox. Could information be preserved somehow, perhaps encoded on the event horizon itself, or slowly radiated back into the universe through Hawking radiation? It's a question that sits at the edge of knowledge, challenging our understanding of reality. Inside, extreme gravitational forces affect every particle. Atoms are torn apart, nuclei collide, and electrons are forced into unimaginably dense configurations. Matter is transformed into states beyond anything we can replicate in a laboratory. Energy densities become enormous, and the interplay between matter, energy, space, and time creates conditions unlike anywhere else in the cosmos. The physics here is a blend of relativity and quantum mechanics, a theater of extremes where classical rules dissolve. Paths through this interior are all inward. Every direction you travel, every trajectory you follow, leads closer to the singularity. Space curves upon itself, and movement toward the center is inevitable. Even light cannot trace a straight line. Every photon spirals inwards, trapped by the gravitational maze. It is a cosmic funnel, relentless and unavoidable, shaping the flow of everything within its grasp. The event horizon, though invisible, acts like a boundary of knowledge. Outside observers can measure mass, spin, and charge, and even detect energetic radiation from the accretion disk. But the interior remains inaccessible. Predictions rely on theoretical physics, mathematics, and imagination. Inside, space-time stretches and compresses, bending in ways that can create phenomena like closed time-like curves, or paths that loop back on themselves in the realm of extreme relativity. Gravity's pull grows with proximity to the singularity. Tidal forces elongate matter, compressing it in directions perpendicular to the fall. Even light, particles, and radiation are subjected to these forces, their trajectories bent, twisted, and ultimately consumed by the singularity. The deeper you go, the stranger the physics. Energy and matter act in ways that defy intuition, and time as measured by any conventional clock becomes meaningless. In some theoretical models, the interior may host quantum effects that prevent true infinities from forming. Loop quantum gravity and string theory suggest that the singularity could have structure at the smallest scales, replacing infinite density with exotic quantized states. These ideas are speculative but provide a glimpse of what the extreme physics inside a black hole might be. It's a realm where space-time is fluid, matter is unrecognizable, and light is imprisoned forever. Every particle, every photon, every fragment of matter crossing the event horizon participates in this cosmic dance. The interplay of time dilation, gravitational warping, and quantum uncertainty creates a space so alien it challenges every instinct, every law, and every equation we use to understand reality. It is not just a hole in space, but a theater of physics pushed to its ultimate limits. A place where imagination and theory collide. Black holes, though often thought of as devouring everything in their path, are not entirely silent in the universe. In 1974, Stephen Hawking made a discovery that changed everything we knew about these cosmic enigmas. He proposed that black holes emit a faint radiation, now called Hawking radiation, caused by quantum fluctuations near the event horizon. This revelation was astonishing. Black holes, long considered the ultimate absorbers, could slowly leak energy and even shrink over unimaginably long timescales. Imagine pairs of virtual particles constantly popping in and out of existence at the edge of the event horizon. One particle falls into the black hole while the other escapes, carrying away a tiny amount of energy. Over billions of years, this process could reduce the black hole's mass, a slow evaporation that spans longer than the current age of the universe for stellar mass black holes. The physics is delicate, subtle, and utterly alien to our everyday experience, but it demonstrates the strange interplay between quantum mechanics and gravity inside and near black holes. Hawking radiation is not visible light in the conventional sense. It is a stream of photons, particles, and possibly other forms of energy, emitted in a manner that is incredibly faint compared to the immense gravity of the black hole itself. Detecting it directly is extraordinarily difficult. Yet, this theoretical radiation has profound implications. It suggests that black holes are not eternal, that the universe has mechanisms to slowly reclaim matter and energy once swallowed. The energy dynamics near a black hole are unlike anything else in the cosmos. As matter falls in, it heats to incredible temperatures, forming accretion disks that glow in X-rays and gamma rays. Magnetic fields twist, matter accelerates, and plasma jets are ejected at near-light speeds along the rotational axis of the black hole. These processes create cosmic lighthouses, visible across vast stretches of the universe, revealing the hidden energy just outside the event horizon. Inside, the relationship between energy, mass, and space-time is even more extreme. Tidal forces stretch matter, spaghettifying everything into streams of energy and particles. Gravitational potential energy converts into heat, radiation, and motion, creating conditions where conventional physics ceases to function normally. It is a place where energy is concentrated beyond comprehension, swirling in a chaotic yet fascinating ballet that bends space and time itself. Even the concept of mass becomes fluid. The energy of matter falling in contributes to the overall mass of the black hole, altering its gravitational pull. Rotation, charge, and mass interact to define the black hole's structure. Rapidly spinning black holes, known as Kerr black holes, create frame-dragging effects, twisting space-time around them in ways that could, in theory, allow for closed loops or extreme gravitational pathways inside. Hawking radiation also raises profound questions about information. If a black hole can slowly lose mass through radiation, what happens to the information about everything it has ever consumed? Quantum theory insists that information cannot be destroyed, leading to what physicists call the information paradox. This paradox drives much of modern black hole research, pushing scientists to explore the boundaries of physics, quantum mechanics, and cosmology. The energy within and around black holes is not only theoretical, it manifests in some of the universe's most spectacular phenomena. Jets shooting from active galactic nuclei, brilliant X-ray emissions, and the swirling dance of accretion disks reveal the dynamic forces at play. The black hole, though invisible, is a generator of energy on scales almost impossible to imagine, influencing galaxies and interstellar environments far beyond its horizon. Even at the smallest scales, quantum effects continue to challenge our understanding. Particles flicker in and out of existence, space becomes granular, and gravity contorts paths of matter and energy into forms we cannot easily visualize. Inside the black hole, energy and matter converge in an intricate, extreme, and unpredictable dance, revealing the universe at its most powerful and strange. As matter plunges toward the singularity, it undergoes one of the most bizarre and extreme phenomena in the universe: spaghettification. The gravitational forces near a black hole are not uniform. They are vastly stronger closer to the singularity than further away. This difference in gravitational pull stretches objects along the direction of the fall while compressing them in perpendicular directions. Imagine a spaceship or a comet being pulled into a black hole. It would be elongated into a thin, almost noodle-like form, stretched and torn apart by tidal forces that are unimaginable in any terrestrial. Even individual particles feel this force. Atoms are pulled apart, nuclei collide, and electrons are forced into denser states. Ordinary matter no longer behaves as it does in familiar conditions. Space itself is distorted around the object, and the concept of volume begins to lose meaning. The forces of gravity dominate all other interactions, bending matter into shapes that defy classical intuition. Time continues to stretch, making the experience entirely alien. This stretching occurs at extreme speeds. As an object gets closer to the singularity, the difference in gravitational pull between its nearest and farthest points becomes enormous. A person falling feet first toward the black hole would have their feet stretched long before the rest of their body, creating an elongation that could extend for kilometers. Everything is pulled inward, drawn relentlessly toward the singularity, and nothing can resist the tidal forces. Spaghettification isn't merely a theoretical concept. It is a natural consequence of general relativity. These forces can stretch entire stars before they are swallowed. When a star ventures too close to a supermassive black hole, it can be ripped apart in a tidal disruption event, with fragments spiraling inward and emitting bursts of radiation visible across galaxies. This is how astronomers can detect black holes indirectly, by observing the catastrophic fate of matter at their edges. Even light is not immune. Photons traveling near the singularity are bent, twisted, and trapped in curved trajectories. The familiar straight-line propagation of light no longer applies. Radiation emitted by falling matter is often pulled into orbit temporarily, creating glowing accretion disks and intense X-ray emissions before ultimately being swallowed. The interplay of gravity and energy produces a cosmic ballet of destruction and illumination, visible across unimaginable distances. The extreme environment also affects quantum particles. Virtual particles pop in and out of existence, influenced by tidal forces and spacetime curvature. The interactions of these particles with the black hole contribute to Hawking radiation, subtly connecting the destructive interior to the energy emitted beyond the event horizon. Matter and energy become deeply entangled with the structure of spacetime itself, a relationship that is both violent and strangely ordered. As spaghettification progresses, the original structure of matter is entirely obliterated. Molecules, atoms, and subatomic particles are all stretched into a singular direction, losing any recognizable form. The interior of the black hole becomes a realm of extreme density and distorted spacetime, where classical concepts of shape, orientation, and volume no longer apply. Everything that enters is transformed into something almost entirely alien, a stream of matter and energy spiraling toward the singularity. Even the most massive objects succumb to these forces. Stars, planets, and gas clouds are shredded and integrated into the black hole's mass. The enormous energy released during this process can power jets of particles and radiation, feeding back into the cosmos in spectacular displays. In this way, the destructive interior of a black hole becomes a source of indirect cosmic illumination, revealing glimpses of its invisible power to the universe outside. Spaghettification is more than just stretching. It is a transformation of reality. Space, time, matter, and energy merge in unprecedented ways. It challenges every concept of physical existence and forces us to imagine a universe where the familiar rules do not apply. Every object, from the smallest particle to the largest star, is reshaped, redirected, and consumed, leaving nothing recognizable behind. Before anything crosses the event horizon, the black hole exerts an almost irresistible pull on surrounding matter, creating what astronomers call an accretion disk. This disk is a swirling maelstrom of gas, dust, plasma, and fragments of stars, spinning at incredible speeds as it spirals toward the singularity. Imagine a cosmic whirlpool, stretching for thousands of kilometers, with matter heated to millions of degrees by friction and gravitational forces. The energy released in this process is staggering, producing X-rays and gamma rays that can be detected across galaxies, offering us the only indirect glimpse into the black hole's immense power. Within the accretion disk, matter is in constant violent motion. Friction and collisions between particles generate tremendous heat, causing plasma to glow intensely. This glow is not uniform. Turbulence, magnetic fields, and instabilities create patterns, jets, and bursts of radiation that seem almost alive. Matter is drawn inward, orbiting faster and faster as it approaches the event horizon, until it crosses the threshold and vanishes from the observable universe. Inside the inner regions of the disk, just outside the event horizon, space-time is so warped that orbital paths are no longer stable in the usual sense. Matter moves in extreme ellipses and spirals, stretched and twisted by the gravitational forces that dominate every interaction. Electromagnetic forces compete with gravity, creating complex flows of charged particles and generating magnetic fields of enormous strength. These magnetic fields can channel some of the material into powerful relativistic jets that shoot away from the black hole's poles at near-light speed. The accretion disk acts as a bridge between the outside universe and the black hole's interior. It is where matter begins its last journey inward, heated, stretched, and transformed before it disappears. While the disk itself exists outside the event horizon, the behavior of matter here gives us clues about the forces and conditions just inside. Studying the radiation and energy released by the accretion disk allows scientists to infer properties of the black hole, including its mass, spin, and even hints about the structure beyond the horizon. Inside the event horizon, matter that once composed the accretion disk undergoes extreme transformations. Compressed by tidal forces, it stretches, collides, and ultimately converges toward the singularity. Time and space are warped to such a degree that any trajectory inevitably leads inward. The material no longer exists in forms familiar to us. Atomic and subatomic structures are destroyed. Matter is squeezed into inconceivable densities, and energy is concentrated in a way that challenges our understanding of physics. The dynamics of the accretion disk also illustrate the immense gravitational influence of the black hole. Orbital velocities near the horizon approach a significant fraction of the speed of light, stretching time and bending paths of particles. Energy radiates outward while matter flows inward, creating a paradoxical system of destruction and illumination. The black hole consumes while simultaneously influencing its surroundings, shaping galaxies and interstellar environments far beyond the event horizon. Jets formed from accretion disk material are among the most spectacular phenomena in the universe. Charged particles, guided by intense magnetic fields, are expelled along the rotational axis of the black hole, traveling thousands of light years into space. These relativistic jets are not just displays of energy. They are a direct consequence of the physics governing matter near the black hole, offering indirect insights into the otherwise hidden interior. Inside the event horizon, the last remnants of the accretion disk are stretched and transformed by spaghettification and extreme gravity. Photons, particles, and even atoms follow paths dictated entirely by the warped geometry of space-time, leaving the universe outside with no trace of their final fate. Yet the energy and radiation released in the process provide a cosmic footprint, hints of the violent and incomprehensible interior. Studying these processes helps us understand the environment just beyond the event horizon, giving us a glimpse of how matter transitions from the observable universe into the singularity. The physics here is extreme, the energy unimaginable, and the transformations profound. Matter is no longer ordinary. It is reshaped, accelerated, and ultimately consumed by the heart of the black hole. Black holes are not silent. They hum and vibrate across the fabric of space-time in ways we can now detect through gravitational waves. These ripples, first observed directly in 2015, originate from massive events like black hole mergers, where two singularities spiral together, warping space and time as they collide. But even inside a solitary black hole, the extreme dynamics of matter and energy can generate turbulence in the surrounding space-time. Imagine the interior as a stormy sea, not of water, but of gravity itself, stretching and bending space in invisible, undulating waves. Matter falling into the black hole contributes to this hidden turbulence. Streams of gas, plasma, and particles spiral inward, accelerated to incredible velocities. The interactions among these streams create fluctuations in gravitational pull, producing localized distortions that propagate through space-time. While we cannot directly observe inside the event horizon, these effects can influence the accretion disk, jets, and even the surrounding cosmic environment, providing subtle fingerprints of the interior activity. As matter nears the singularity, tidal forces grow extreme. The intense stretching and compressing create chaotic interactions between particles and radiation. Photons trapped near the core bend, twist and orbit in complex paths, colliding with other photons and particles. These interactions can generate bursts of energy and turbulence that reverberate outward, influencing how matter enters the black hole and potentially affecting how energy escapes in the form of Hawking radiation. Gravitational waves produced inside black holes are fundamentally different from those observed from mergers. They are minute fluctuations in the curvature of space-time caused by internal dynamics, stretching and compressing space at incredibly small scales. The mathematics predicts that as matter spirals inward, it can create oscillations in the fabric of space-time that propagate toward the singularity, forming complex, turbulent patterns. These patterns are like the heartbeat of the black hole, a rhythm of energy, gravity, and extreme physics beyond the event horizon. The singularity itself adds to this turbulence. As the core of the black hole contains mass in an unimaginably small volume, the gravitational field is infinite in classical terms. This means that even the tiniest displacement of matter can cause enormous fluctuations in space-time curvature. Inside, space and time lose their conventional meaning, and energy and matter interact in ways that defy any terrestrial analogy. The interior is a realm where chaos and extreme order coexist in a delicate, violent balance, a storm invisible yet overwhelmingly powerful. The intense spinning of rotating black holes, or Kerr black holes, contributes further to this turbulence. Frame-dragging effects twist space-time, forcing everything inside to rotate along with the singularity. Particles, light, and radiation caught inside experience spiraling paths, moving along warped trajectories dictated by gravity and rotation. This creates internal turbulence unlike anything seen elsewhere. A cosmic maelstrom of motion, acceleration, and distortion that challenges the limits of imagination. Even hypothetical paths through the interior are chaotic. Closed time-like curves, predicted in certain solutions of general relativity, suggest that inside a spinning black hole, matter could in theory loop back on itself along warped space-time trajectories. These extreme possibilities demonstrate that the black hole interior is not static. It is a dynamic, turbulent environment where energy, mass, and the geometry of space-time interact in ways that cannot exist anywhere else in the universe. Magnetic fields, although originating outside the horizon, influence internal dynamics indirectly through the behavior of infalling matter. Charged particles follow twisted paths along the gravitationally warped spacetime, creating internal currents and energy flows that interact with the curvature. Inside, this may produce patterns of turbulence that ripple across matter and energy, amplifying chaos while obeying the underlying geometry of the black hole. The interior is a place where classical physics meets quantum extremes. Matter and radiation interact in ways that produce turbulence across scales, from the tiniest particle fluctuations to massive flows of energy spiraling toward the singularity. Gravity dominates, yet energy and quantum effects constantly shape the internal environment, creating a realm of hidden motion, invisible storms, and space-time upheavals that remain beyond direct observation. Inside a black hole, the extreme gravity warps not only space and time, but also the very quantum fabric of reality. At scales approaching the singularity, particles behave in ways that challenge our conventional understanding of matter. Electrons, protons, and neutrons no longer follow ordinary rules. Quantum fluctuations dominate, creating unpredictable bursts of energy and ephemeral particles that appear and vanish in fractions of a second. The black hole interior becomes a stage where quantum mechanics and relativity collide in their most extreme forms. Virtual particles, constantly appearing and disappearing, interact with the collapsing matter in ways that are almost impossible to visualize. Some are drawn inward toward the singularity, others momentarily interact and vanish, and some may contribute to Hawking radiation that escapes from near the event horizon. These quantum effects suggest that even in the darkest heart of a black hole, there is an ongoing dynamic interplay of matter and energy, a chaos that obeys probabilistic rules rather than deterministic ones. Time itself is altered by these quantum interactions. From an outside perspective, anything crossing the event horizon seems frozen. Yet at the quantum level, particles vibrate, oscillate, and interact endlessly. These interactions may influence the structure of the singularity, the behavior of infalling matter, and even the nature of space-time itself. The quantum world inside a black hole is one where uncertainty reigns supreme, where nothing is fixed, and where the fundamental nature of reality is constantly in flux. One fascinating question arises: could the quantum structure inside a black hole preserve information? Classical physics suggests everything is lost, but quantum mechanics insists that information cannot be destroyed. This has led to ideas such as the holographic principle, which proposes that the information about matter falling in might be encoded on the event horizon rather than being obliterated at the singularity. Inside, particles continue to interact, yet the ultimate fate of information remains one of the deepest mysteries of physics. Energy at the quantum level behaves differently under the extreme gravity of a black hole. Particle collisions are amplified, creating bursts of energy that, if they could be observed, would seem like flashes of creation and destruction happening simultaneously. Quantum tunneling may allow particles to escape, contributing to subtle energy emissions, though nothing can cross back beyond the horizon fully. The interior is a place where energy transforms, oscillates, and interacts in ways that defy classical intuition. Even the concept of distance and size is warped. The Planck scale, the smallest scale of meaningful physics, becomes crucial. Below this scale, space-time may be granular, like a lattice, and particles may not exist as discrete points, but as probability clouds. Inside a black hole, these quantum effects are magnified by gravity, producing interactions that are entirely alien to human experience. Matter and energy become intertwined with space-time in ways that suggest the singularity itself may not be a simple point, but a complex quantum structure. The warping of space-time also affects particle spin, entanglement, and decay rates. Particles behave differently under intense gravity, sometimes accelerating decay, sometimes preventing interactions that would normally occur. The interior of the black hole is a laboratory of extremes, revealing the interplay between the forces of nature in their most intense form. Here, general relativity and quantum mechanics collide, creating phenomena that may never be fully comprehensible, but are essential to understanding the ultimate nature of reality. Quantum fluctuations may also interact with gravity to produce small-scale turbulence within the black hole. This turbulence affects matter falling in, the geometry of space-time, and even the emission of energy that can influence Hawking radiation. Though invisible to outside observers, these internal quantum dynamics are a crucial part of what makes black holes so mysterious, demonstrating that even in the heart of darkness, physics continues to dance, shift, and evolve. In this extreme environment, matter, energy, and information exist in states that are fundamentally different from anything observable elsewhere in the universe. Each particle's trajectory, interaction, and transformation is dictated by an intricate balance of gravitational and quantum forces. The black hole interior is a realm of constant motion, uncertainty, and transformation, where classical physics dissolves and quantum reality reigns, revealing a world both alien and profoundly fascinating. As matter plunges deeper toward the singularity, familiar atomic structures cannot survive. Electrons are stripped from atoms, nuclei collide, and ordinary matter transforms under extreme pressure into exotic states that exist nowhere else in the universe. One possibility is neutronization, where protons and electrons merge to form neutrons, creating a super-dense neutron-rich environment. Imagine a substance so dense that a teaspoon of it would weigh billions of tons, compressed into a volume almost beyond comprehension. Even beyond neutron matter, physics predicts the formation of quark-gluon plasma, a state where quarks, the fundamental building blocks of protons and neutrons, roam freely, unbound by the forces that normally hold them together. This plasma represents one of the most extreme forms of matter theorized, existing only under the unimaginable densities and temperatures inside a black hole. Here, particles interact with incredible energy, colliding and combining in ways that stretch the limits of quantum mechanics. The singularity itself may host even stranger configurations. Some theories suggest that matter could exist in forms we cannot yet imagine, where the boundaries between particles, energy, and space-time dissolve. The density and gravity are so extreme that the traditional definitions of mass, volume, and distance break down. Here, space-time curvature becomes infinite in classical terms, that quantum mechanics hints at a discrete structure, perhaps replacing the singularity with something resembling a quantum foam. Temperature inside the black hole rises to levels beyond comprehension. Matter is heated not just by compression, but by the energy of tidal forces, particle collisions, and gravitational interactions. Particles are accelerated to near-light speeds, forming streams of energy and dense matter spiraling toward the core. Every collision and interaction produces bursts of radiation, trapped forever inside the event horizon, creating a hidden inferno of physics at its most extreme. Neutron stars outside black holes provide a window into what this matter might look like, though the conditions inside a black hole surpass even the densest neutron star. Magnetic fields, particle spin, and relativistic effects all contribute to the exotic behavior of matter. Within the black hole, these effects are amplified, creating complex patterns of motion, turbulence, and interaction at scales both microscopic and macroscopic. Theoretical particles, predicted by high-energy physics, may also exist inside black holes. Strange quarks, hyperions, and other exotic constituents could emerge under extreme pressure. These particles interact in ways that challenge conventional understanding, creating a dense dynamic interior where the familiar categories of matter, solid, liquid, gas, plasma no longer apply. Every particle is part of an intricate, energetic dance dictated by gravity, quantum mechanics, and the curvature of space-time. Infalling matter continues to be spaghettified and compressed as it encounters these exotic states. Streams of particles are stretched into elongated forms, colliding and merging, producing bursts of energy and complex quantum interactions. This interior environment is dynamic and ever-changing, a realm where particles, energy, and space-time are intertwined in a way impossible to replicate elsewhere. Rotation adds another layer of complexity. In spinning black holes, frame dragging twists matter and energy, creating vortices of exotic particles and plasma. These spiraling motions may interact with the quantum and gravitational turbulence, forming an intricate internal pattern of flows, oscillations, and energy exchanges that are entirely invisible to the outside universe. Even the most extreme matter cannot resist the singularity's pull. Every particle, every quark, every fragment of energy continues its inexorable journey inward. Here, inside the black hole, matter exists in states beyond ordinary experience, moving and transforming according to laws that challenge the very definitions of reality. It is a place of extraordinary density, immense energy, and unparalleled mystery, revealing the hidden depths of the universe's most enigmatic objects. The interior of a black hole is not uniform. It has layers, each with distinct properties shaped by gravity, energy, and matter. Beyond the event horizon, the outer layer consists of matter recently captured by the black hole's immense pull. Gas, dust, and photons spiral inward, forming chaotic streams that twist under the influence of gravity. This outer region is still dynamic, with matter interacting with itself, photons and magnetic fields, creating turbulence and flow that ripple inward toward the core. Deeper inside, the matter becomes denser, compressed by the black hole's gravity to the point that atomic structures cannot survive. Electrons merge with protons, forming neutron-rich regions in a superdense state of matter. Particles collide at near-light speeds, releasing energy in bursts that reverberate through the surrounding layers. These mid-interior regions are a tumultuous sea of compressed matter, extreme pressure, and high-energy interactions, forming the hidden core dynamics that drive the black hole's interior evolution. Moving even closer to the singularity, exotic forms of matter dominate. Quarks, gluons, and possibly even more exotic particles exist in a free, high-energy plasma, moving in ways that defy conventional physics. Space-time itself is bent to the extreme, creating distortions that affect how matter and energy interact. The internal structure here is not static. Currents, vortices, and collisions continually reshape the environment, producing layers within layers of energetic, dense material, all drawn inexorably inward. The interaction of rotation adds another layer of complexity. In spinning black holes, frame dragging twists matter and radiation into spiraling paths, creating vortex-like structures within these layers. Matter does not fall straight toward the singularity. It follows twisted trajectories influenced by both rotation and gravity, producing internal patterns of motion that are complex, dynamic, and invisible to the outside universe. The interior is therefore a multi-dimensional, rotating system of matter and energy streams. Photon behavior in these layers also shapes internal dynamics. Light cannot escape, but it interacts with matter and fields, bouncing, scattering, and colliding in patterns that contribute to turbulence and energy redistribution. These trapped photons carry energy through the interior, influencing particle trajectories and pressure gradients, creating a layered interior where energy flows in ways that are fundamentally different from anything outside the black hole. Tidal forces are particularly pronounced in the deeper layers. Spaghettification stretches matter into elongated forms, separating particles across distance scales that vary depending on depth. Near the singularity, these effects reach extremes, with objects stretched and compressed simultaneously, producing chaotic motion and extreme energy interactions. Every layer closer to the core experiences more intense gravitational gradients, shaping the internal environment continuously. Quantum fluctuations permeate each layer. Virtual particles emerge and vanish, interacting with the high-density matter and energetic photons. These fluctuations are amplified by the gravitational field, producing microbursts of energy and subtle turbulence. In combination with relativistic effects, these quantum processes shape the interior structure, making each layer a dynamic mix of matter, energy, and space-time distortions. Magnetic and gravitational fields interact with the layers, generating currents and flows that guide particle motion. Charged particles spiral along field lines, producing internal currents that interact with surrounding matter and energy. These fields create internal patterns, hidden vortexes, and energetic loops that structure the interior, linking each layer with the next through dynamic interactions of matter and energy. Pressure, density, and energy vary across layers, producing gradients that drive the motion of matter inward. Matter and energy streams continuously feed the singularity, with interactions between layers creating turbulence, heating, and particle acceleration. The interior is thus not a static void, but a living system of layers, each feeding into the next, all ultimately converging on the singularity. Even though these layers are invisible to the outside universe, their dynamics govern the behavior of the black hole as a whole. From the accretion of matter at the outer edges to the extreme physics near the core, the layered structure creates a hidden ecosystem where energy, matter, and space-time interact in complex, continuous patterns. Each layer is both a stage and a participant in the internal story of the black hole, forming a multi-dimensional environment that challenges imagination and stretches the boundaries of physics. At the very heart of a black hole lies the singularity, a point where the familiar rules of physics dissolve, and the universe behaves in ways that are almost impossible to imagine. Gravity here is infinite in classical terms, pulling everything relentlessly toward a single point. Space and time, which we experience as distinct and flowing, collapse into a state where direction, distance, and duration lose all meaning. The singularity is a place where matter, energy, and space-time converge in a dense, incomprehensible nexus, a cosmic endpoint that defies intuition. The interior approaching the singularity is a chaotic arena of extreme forces. Matter is compressed beyond atomic structure. Particles collide at unimaginable energies, and the very fabric of space-time is contorted into forms no observer could witness. The laws of general relativity predict infinite curvature here, while quantum mechanics suggests a granular structure that could replace the classical singularity. The intersection of these two realms is one of the greatest mysteries in modern physics, a puzzle at the frontier of our understanding. Rotation adds further complexity. In spinning black holes, known as Kerr black holes, the singularity may take on a ring-like shape, creating regions where theoretical paths of matter and energy can loop or spiral endlessly. Frame dragging causes spacetime itself to twist, pulling infalling particles along with it in spirals and vortices. Matter does not fall straight inward, but follows these warped trajectories, stretching and colliding in a dynamic ballet before reaching the ultimate core. Time becomes a slippery concept. From an outside perspective, matter appears to slow and freeze as it approaches the horizon. But inside, near the singularity, time may act in non-linear ways. Past, present, and future are no longer clearly defined. Particle interactions, quantum fluctuations, and gravitational dynamics unfold in ways that challenge every assumption about causality and order. The singularity is not just a location. It is a realm where reality itself is warped and folded. Energy density at the singularity reaches extremes that dwarf anything in the observable universe. Every particle, every photon, every fragment of infalling matter contributes to this immense concentration. The interactions of these particles are magnified, producing turbulent, high-energy flows that may ripple through the surrounding interior before ultimately merging with the core. In this region, energy and matter are indistinguishable from the curvature of space-time itself, creating a unified, almost incomprehensible field of existence. Quantum effects at the singularity hint at possibilities beyond current understanding. Virtual particles, quark gluon plasma, and exotic states of matter interact in unpredictable ways. The classical notion of a point of infinite density may be replaced by a quantum structure, where probabilities dictate the behavior of matter and energy. Some theories even suggest connections to other universes or hidden dimensions, though these ideas remain speculative, illustrating just how mysterious this interior truly is. Tidal forces reach their peak at the singularity. Any object, no matter its size, is stretched and compressed beyond recognition. Even elementary particles are distorted by the curvature of space-time, producing effects that challenge intuition and experimental verification. The singularity is a laboratory of extremes, a natural phenomenon where matter, energy, and the geometry of the cosmos interact in ways that cannot be reproduced anywhere else. Despite its inaccessibility, the singularity has indirect effects observable from the outside. Its immense gravity shapes accretion disks, influences relativistic jets, and bends light in ways that reveal its presence. The hidden dynamics at the core determine how matter and energy behave around the black hole, shaping the cosmos far beyond the event horizon. Every particle spiraling inward is influenced by the singularity, making it the ultimate puppet master of the black hole's interior. The singularity also challenges the limits of scientific imagination. It forces physicists to consider unified theories that bridge quantum mechanics and general relativity. The mysteries of this interior matter crushed to extremes, space-time distorted beyond recognition, energy concentrated beyond comprehension, are at the cutting edge of human understanding. It is a realm where science confronts the ultimate unknown, a space where conventional physics gives way to possibilities as strange and exotic as the universe itself. In the depths of a black hole, the singularity is the ultimate endpoint. It is the destination of matter, energy, and even time itself. A realm of extreme density, infinite gravity, and profound mystery. Inside, reality stretches and twists, revealing the universe at its most powerful, most alien, and most intriguing. Every journey inward, every particle falling toward this core, becomes part of a story written in space-time itself. A story that remains hidden, yet exerts its influence across the cosmos. Inside a black hole, one of the most fascinating and perplexing questions arises. What happens to information? In classical physics, when matter crosses the event horizon, it is considered lost forever, absorbed into the singularity. But quantum mechanics insists that information cannot be destroyed. This apparent contradiction has puzzled scientists for decades, creating what is famously known as the black hole information paradox. Inside, matter is crushed, stretched, and transformed. Yet the question lingers. Can the universe somehow remember what has fallen in? As particles spiral inward, their positions, energies, and states are encoded in the fabric of space-time. Even if they are obliterated physically, some theories suggest that their information is preserved at the event horizon in a holographic form. The idea, known as the holographic principle, proposes that the three-dimensional interior of a black hole might be represented as a two-dimensional projection on its surface. Matter inside continues its violent journey toward the singularity, that the information about its properties could be recorded at the edge, like a cosmic ledger of everything that has ever entered. Quantum entanglement further complicates the picture. Particles inside the black hole may remain entangled with partners outside, creating correlations that span the event horizon. These hidden connections suggest that even within the dark, high-gravity interior, the universe maintains subtle links between inside and out. The tangled web of entangled particles forms a network of information, a ghostly fingerprint that might defy the apparent destruction caused by gravity. Hawking radiation, though originating near the horizon, may carry away hints of the internal state. Virtual particles popping in and out of existence interact with the black hole's gravitational field, potentially encoding fragments of information into the escaping radiation. This creates a strange connection. Even as matter disappears inside, the black hole's exterior emits energy that might whisper secrets about the hidden interior. Observers outside could, in theory, detect clues. Although the process is subtle, probabilistic, and extraordinarily difficult to decipher. Inside, the interplay of gravity and quantum mechanics creates extreme uncertainty. Particles cannot be localized in the conventional sense. Their positions, momenta, and energies fluctuate according to quantum rules, stretched and twisted by the immense curvature of space-time. Every interaction is influenced by the singularity's gravitational pull, forming a chaotic and ever-changing environment where information is encoded, transformed, and potentially preserved in ways we barely understand. The paradox challenges fundamental assumptions about the universe. If information is truly lost, it contradicts the core principles of quantum mechanics. If information is preserved, it suggests a hidden order inside black holes that defies classical intuition. The interior, though unobservable, is central to this cosmic puzzle. Every particle, photon, or quark falling inward participates in this intricate dance, contributing to a hidden ledger of the universe's history. Mathematical models of black hole interiors attempt to reconcile these extremes. Some propose that the singularity may not be a true point of infinite density but a quantum structure where information is diffused across the core. Others suggest that space-time inside is foamy, chaotic, and fractal-like, encoding matter and energy in complex patterns that persist despite classical destruction. In this way, the interior becomes a realm where information and matter interact under rules entirely alien to our everyday experience. Even hypothetical wormholes or connections to other universes have been considered as possible ways information might escape. These ideas, though speculative, highlight how the black hole interior is not a passive void but an active participant in the universe's fundamental structure. Matter, energy, and information converge and interact, creating a hidden web of complexity that challenges every assumption about reality. Inside, the journey of information is entwined with extreme forces, spaghettification, quantum fluctuations, and gravitational distortions. Each particle falling inward contributes to the mystery, becoming part of a story that is encoded, scrambled, and transformed in ways that may leave an imprint outside the event horizon. This hidden narrative is one of the most compelling aspects of the black hole interior, suggesting that even in ultimate darkness, the universe may be recording its history in patterns beyond our perception. The information paradox reminds us that black holes are not simply destructive. They are arenas of extreme physics, where matter, energy, and information are entangled in profound, unknowable ways. Inside, the laws of nature converge at their limits, producing phenomena that stretch imagination challenge understanding, and hint at a deeper order hidden within the cosmic darkness. Inside a black hole, time behaves unlike anything experienced in everyday life. As matter approaches the event horizon, time relative to an outside observer slows dramatically. From the perspective of someone falling inward, however, time feels continuous. Yet even within this subjective experience, as one moves deeper toward the singularity, time begins to warp in extreme ways, twisted and stretched by the overwhelming curvature of space-time. Seconds, minutes, and hours lose their conventional meaning, becoming relative measures dictated entirely by the black hole's gravity. The warping of time is not just a theoretical concept. It has real consequences for matter and energy inside. Processes that normally occur at predictable rates, like atomic interactions or particle decay, are altered by the intense gravitational field. Electrons, protons, and even more exotic particles behave differently, moving, colliding, and interacting according to timelines that are incomprehensible outside the horizon. Here, the very rhythm of the universe is reshaped, a cosmic dance choreographed by the immense pull of gravity. Approaching the singularity, tidal forces stretch and compress objects in both space and time. Spaghettification is not just a spatial effect. It is temporal as well. One end of an object can experience time at a vastly different rate than another, producing distortions that ripple through matter, energy, and even the quantum fluctuations surrounding it. The flow of time inside a black hole is not linear, but a complex, warped continuum where cause and effect are bent and twisted by the gravitational landscape. Relativistic effects compound this temporal distortion. Inside a rotating black hole, frame-dragging twists not only space, but also the local flow of time. Particles spiral along trajectories, where time may advance faster or slower depending on position and velocity relative to the singularity. The internal environment is a dynamic interplay between gravity and relativity, producing a temporal landscape as intricate and chaotic as the turbulent matter it contains. Quantum mechanics further complicates the passage of time. Virtual particles appear and vanish on infinitesimal timescales, and their interactions within falling matter can create bursts of energy, shifts in momentum, and local perturbations in space-time. These fluctuations, when amplified by gravity, produce temporal anomalies, stretching the concept of now into a continuum that defies ordinary comprehension. Time becomes a flexible, malleable dimension rather than a fixed progression. Even light, the fastest traveler in the universe, experiences time differently inside a black hole. Photons trapped near the singularity are caught in curved paths, spiraling endlessly and interacting with other particles in ways that create interference patterns invisible outside. The journey of light inside is a journey through warped time, revealing the strange reality of a universe where every moment is simultaneously stretched, compressed, and entangled with every other. For observers outside, this warping is reflected in what is seen at the event horizon. Matter appears frozen, fading slowly, emitting redshifted light, as if time itself is slowing to a crawl. But from the perspective within, processes continue at their own pace, though stretched and twisted by the extreme curvature. The interior is a theater of temporal distortion, where relativity and quantum physics together produce a flow of time entirely unlike the steady tick experienced elsewhere in the cosmos. The consequences for matter and energy are profound. Particle interactions, chemical bonds, and quantum states evolve under this warped time, creating conditions that would be impossible anywhere else. Spacetime itself acts like a fluid medium, bending and folding, allowing matter to exist in states that straddle the boundary between classical behavior and quantum uncertainty. Inside, time is no longer a simple progression, but a dynamic, integral part of the black hole's extreme physics. In the core, near the singularity, these distortions become absolute. The closer one gets, the more time and space intertwine, forming a continuum where distance, duration, and sequence lose all conventional meaning. Every particle and every fluctuation is subject to this warping, creating a reality where past, present, and future are inseparably bound together in a gravitational dance. Time inside the black hole is no longer a measure, but a dimension of extreme complexity, a fundamental element of the singularity's nature. The warping of time also influences how energy, radiation, and matter interact with each other inside. Collisions, particle creation, and quantum fluctuations occur under temporal conditions that are inconsistent with the outside universe. This internal time landscape shapes the black hole's interior dynamics, governing the behavior of everything within while remaining hidden from external observation. Inside, the black hole is a realm where time itself becomes a fluid, dynamic and enigmatic force entwined with the deepest mysteries of space, matter, and energy. Inside a black hole, light no longer travels in straight lines as it does in ordinary space. Photons are trapped by the immense gravity, following twisted, spiraling paths that bend and loop endlessly. Imagine a labyrinth of light where every photon is caught in a gravitational dance, circling, colliding, and occasionally interacting with other particles and radiation streams. The interior is a place where the familiar rules of optics are completely transformed, creating patterns of motion that are invisible to outside observers, but crucial to the black hole's internal dynamics. As photons fall inward, they experience extreme gravitational redshift. Their wavelengths stretch, energy diminishes, and yet their interactions with matter remain intense. They can collide within falling particles, contributing to localized bursts of energy and radiation. These collisions are amplified by the curvature of space-time, creating a chaotic, luminous environment at scales far beyond normal perception. Though we cannot see it, the interior of a black hole is alive with the motion of light, energy, and matter entwined in a cosmic ballet. Frame dragging in rotating black holes twists the paths of photons even further. Light does not simply fall toward the singularity, but follows spiral trajectories dictated by the black hole's spin. This rotation creates vortices of trapped light, circling the singularity in complex, dynamic patterns. Some photons may orbit for extended periods before being absorbed, contributing to the turbulent energy environment within. The interior becomes a three-dimensional storm of photons, matter, and gravitational forces, all interacting continuously in ways that challenge human imagination. Photons also interact with quantum fluctuations inside the black hole. Virtual particles popping in and out of existence affect photon trajectories, causing scattering, energy shifts, and bursts of radiation. These effects are magnified by the extreme gravitational field, producing a chaotic interplay of light and matter that is completely hidden from the outside universe. The interior is a theater where light is both particle and wave, both energy and messenger, tracing paths through a distorted, dynamic space-time. Even near the singularity, photons may experience paths that loop, cross, or spiral unpredictably. Light can, in theory, be caught in closed time-like curves inside rotating black holes, creating trajectories that challenge conventional notions of cause and effect. Photons become participants in the extreme physics of the interior, their paths determined not only by gravity, but by the complex interplay of quantum and relativistic effects. Every ray of light contributes to the hidden dynamics, carrying energy, influencing matter, and weaving through the fabric of space-time. Inside, light interacts with exotic states of matter, including neutron-rich cores and quark-gluon plasma. These interactions create bursts of radiation, energy exchanges, and scattering events that feed the turbulent internal environment. Photons may collide with particles at near-light speeds, producing chaotic motion that propagates across the interior. The dynamics of light are central to the behavior of the black hole, shaping energy distribution, particle interactions, and the motion of matter falling toward the singularity. The paths of photons also determine the internal feedback between matter and radiation. Energy from infalling light can influence particle trajectories, create localized turbulence, and interact with quantum fluctuations. These interactions are ongoing, producing a dynamic, ever-changing environment where energy, matter, and light are inseparably linked. Inside the black hole, the journey of photons is both chaotic and structured, forming patterns that are hidden yet fundamental to the interior physics. Even though light cannot escape beyond the event horizon, its behavior inside affects the black hole's external features. Accretion disks, relativistic jets, and radiation emissions all carry imprints of the internal dynamics of photons and their interactions. The interior is therefore not isolated in effect. It shapes the environment outside in subtle but measurable ways. Every photon trapped inside participates in the creation of this hidden energy ecosystem. Ultimately, the interior of a black hole is a realm where light is transformed by extreme gravity and quantum effects. Its paths are twisted, spiraling, and unpredictable. Photons interact with matter, radiation, and space-time itself, creating an environment that is both turbulent and highly structured. The journey of light inside is a glimpse into a hidden universe where physics is pushed to its absolute limits. A dance of energy, matter, and space-time at the edge of human comprehension. Inside a black hole, energy moves in ways that defy conventional understanding. Matter plunging toward the singularity carries enormous kinetic energy, while gravitational potential energy transforms into heat, radiation, and particle motion. Streams of infalling matter create turbulent currents, interacting with photons, quantum fluctuations, and the exotic states of matter already present. The interior is alive with motion, a hidden ocean of energy swirling in patterns dictated by gravity, relativity, and quantum rules. Accretion dynamics within the black hole are not confined to the event horizon. As particles fall inward, they form dense, rotating streams that collide and spiral, producing localized bursts of energy. These collisions amplify pressure and heat, influencing neighboring particles and photons. Even though external observers cannot see these internal flows, they shape the black hole's overall behavior, determining how energy is distributed and how matter interacts within this extreme environment. Tidal forces stretch and compress matter, converting spatial deformation into energy. Spaghettification is both a physical and energetic transformation. A falling object is elongated, its internal particles accelerated, and its energy redistributed across the interior. Energy is constantly being transformed between forms: kinetic, potential, thermal, and quantum, creating a dynamic, ever-changing environment where the laws of classical physics blend with relativistic and quantum effects. Particle acceleration is extreme. Infalling matter is boosted to velocities approaching the speed of light, colliding with other streams of matter, photons, and virtual particles. Each collision releases energy in unpredictable ways, forming chaotic internal currents. These interactions amplify turbulence, create pressure waves, and induce localized radiation bursts that remain trapped inside, fueling a hidden ecosystem of energy and motion. Rotation complicates the picture further. In Kerr black holes, frame-dragging twists energy flows into spirals, forming vortices where matter and photons circulate endlessly before ultimately reaching the singularity. These spiraling currents interact with quantum fluctuations, exotic matter, and intense gravity, producing a multi-layered internal system of energy transfer. The black hole interior becomes a complex interplay of motion, force, and transformation that is both chaotic and structured. Quantum effects modulate these energy flows. Virtual particles pop in and out of existence, exchanging energy within falling matter. The superdense interior amplifies these interactions, creating bursts of energy on scales far beyond ordinary physics. The interplay between gravity, quantum fluctuations, and particle collisions produces internal turbulence, forming patterns that are dynamic, complex, and fundamentally alien to external observers. Temperature variations inside the black hole are extreme. Some regions may reach levels hotter than the cores of stars, while other areas, influenced by quantum fluctuations, experience different energetic states. These variations create gradients that drive further flows of energy, accelerating particles, twisting matter, and feeding the dynamic processes that define the interior environment. The black hole is not a static void. It is a storm of energy in constant motion. Even light, trapped within the event horizon, contributes to energy flows. Photons collide with matter, scatter, and transfer energy through interactions with particles and fields. These collisions generate localized turbulence, feeding the dynamic system and influencing the behavior of matter and energy further inward. The paths of photons, matter streams, and quantum fluctuations are intertwined, forming a feedback loop that perpetuates energy circulation inside. The interplay of energy, matter, and gravity also creates hidden structures. Vortices, currents, and chaotic flows form in the interior, shaping particle trajectories and influencing the transformation of matter into exotic states. Energy is constantly redistributed, with bursts, flows, and collisions driving the evolution of the interior environment. Each stream of energy contributes to the hidden physics of the black hole, a realm entirely disconnected from the observable universe. The black hole interior is a place where energy is alive. It moves, interacts, and transforms in ways unimaginable outside the event horizon. Currents of matter, photons, and quantum effects twist, spiral, and collide, forming a dynamic, high-energy ecosystem that powers the hidden heart of the black hole. It is a realm of motion, transformation, and complexity, where the laws of physics operate at their most extreme, revealing a universe within a universe, hidden from view, but fundamental to the cosmos itself. Inside a black hole, the seeds of what become relativistic jets outside are already present, shaped by extreme gravity, rotation, and the interactions of magnetic fields within falling matter. These jets, seen as streams of energy shooting into space at near light speeds, have their origins deep within the interior. Matter spiraling inward is accelerated, twisted, and organized by forces that are invisible yet powerful, forming hidden channels of energy that ultimately influence the cosmos beyond the event horizon. As matter falls toward the singularity, it interacts with spiraling magnetic fields, gaining angular momentum and energy. Charged particles accelerate along these lines, forming intense focused currents. Inside, these processes are chaotic yet structured, creating a dynamic interplay between gravity, rotation, and magnetism. The jets that may emerge outside are thus rooted in the hidden orchestration of the black hole's interior, where energy is guided and concentrated along invisible paths. Relativistic effects inside play a major role. Frame dragging caused by the black hole's spin twists spacetime itself, pulling matter and energy along curved trajectories. This twisting guides in falling particles into patterns that resemble the spiraling nature of jets observed outside. The interior becomes a laboratory of acceleration, where kinetic energy, gravitational pull, and magnetic forces combine to create flows capable of punching through the surrounding accretion disk once they escape the event horizon. Turbulence inside is immense. Collisions between infalling matter, photons, and virtual particles produce high-energy interactions that amplify motion along the magnetic channels. These energetic bursts feed the jets, creating concentrated streams of matter and radiation spiraling inward before ultimately escaping outward as structured, observable phenomena. The interplay of chaos and order defines how energy is distributed and funneled inside. Photons are also participants in these hidden dynamics. Trapped light follows curved paths influenced by magnetic fields and gravity, transferring energy through collisions and interactions with matter. These photon streams contribute to the internal momentum and the development of focused currents that may later emerge as part of the relativistic jets. Even the movement of light inside is sculpted by the black hole's extreme conditions. Rotation amplifies energy concentration. In spinning black holes, the interior forms complex vortices where matter, photons, and energy circulate, accelerating along magnetic paths. These vortices act like hidden engines, powering the internal currents that eventually feed the jets outside. The spiraling motion of matter and energy inside provides both structure and energy to the system, connecting the unseen interior with observable phenomena far beyond the event horizon. Quantum fluctuations add another layer of complexity. Virtual particles popping in and out of existence interact with matter and radiation in these spirals, injecting bursts of energy that modify particle trajectories and influence momentum flows. The black hole interior is therefore a cauldron of interacting forces, where quantum mechanics, relativity, and classical physics converge to produce conditions that define the hidden dynamics of jet formation. Even gravitational waves may subtly influence these interior flows. Infalling matter and energy generate ripples in spacetime, perturbing the paths of particles and photons. These interactions contribute to the turbulence and structure of the internal energy currents, amplifying motion along spiraling paths. Every particle, every photon, every quantum fluctuation plays a role in shaping these hidden conduits of energy. Inside the black hole, these nascent jets are not visible but are active, forming energetic highways that carry momentum, particle flux, and radiation along defined paths. They represent an internal choreography, a system of energy flow guided by gravity, magnetism, and rotation, hidden from the outside world yet fundamentally connected to what may be observed far away. The interior of a black hole is a place where energy, matter, and light converge to create pathways that extend beyond mere absorption. Relativistic jets are born from this hidden orchestration, shaped by the interplay of extreme forces, spinning vortices, magnetic lines, and turbulent flows. Inside, the black hole is not just a void but a dynamic, structured, high-energy environment, orchestrating phenomena that ripple across the cosmos. Inside a black hole, magnetic fields are extreme, invisible forces shaping the behavior of matter, light, and energy. As charged particles spiral inward, these fields twist and intensify, forming complex networks that influence the movement of everything inside. Imagine streams of particles caught in invisible threads, guided and stretched by these forces, creating a hidden lattice of energy and motion that governs the internal environment in ways we are only beginning to theorize. The rotation of a black hole amplifies magnetic fields through frame dragging, creating spiraling vortices where energy and matter follow twisted paths. Particles moving along these magnetic lines experience acceleration, collisions, and energy transfer, contributing to the turbulent currents inside. The magnetic field acts like a hidden skeleton, organizing the chaotic motion of matter and radiation into patterns that persist despite the extreme conditions surrounding them. Magnetic reconnection occurs deep inside, where magnetic field lines break and reconnect, releasing bursts of energy. These events can accelerate particles to near-light speeds, create localized heating, and generate internal turbulence. Unlike solar flares observed on stars, these processes inside a black hole are amplified by the overwhelming gravity and density, producing energy exchanges far beyond anything encountered elsewhere in the universe. The interior fields interact with the exotic states of matter present. Neutron-rich cores, quark gluon plasma, and even potential unknown particles are influenced by these magnetic forces, which twist, compress, and accelerate them. The interactions are complex, creating feedback loops where particle motion reinforces field strength and vice versa. It is a dynamic, self-organizing system that continuously shapes the interior environment. Magnetic fields also affect the paths of photons and other radiation trapped inside. Light can be guided, twisted, and refracted by these invisible lines, creating spirals, vortices, and interference patterns that influence energy distribution. Every photon, every particle is subtly guided by the unseen architecture of magnetism, producing a hidden dance of motion, energy, and interaction that continues relentlessly toward the singularity. The strength of these fields near the singularity becomes almost unimaginable. Gravity compresses matter to extreme densities, intensifying magnetic flux and creating forces that dominate local dynamics. Particles cannot move freely, but are bound to spiraling, twisting trajectories along these lines. The interior becomes a turbulent maze of energy, where magnetic structure, gravitational pull, and particle dynamics intertwine to create a constantly evolving environment. Magnetic turbulence may also connect different regions inside the black hole. Currents, vortices, and reconnections could form conduits of energy that transport momentum and influence particle motion across the interior. Even though this energy remains trapped within the event horizon, it structures the internal dynamics, creating localized flows, hotspots, and interactions that shape the journey of every infalling particle. Quantum effects are further amplified by magnetic forces. Virtual particles, exotic matter, and quantum fluctuations respond to these intense fields, producing localized bursts of energy and altered trajectories. Magnetic influence on quantum processes creates patterns of interaction that are unique to black holes, pushing both classical and quantum physics to their limits. Rotation and magnetism together can produce structures resembling internal jets or spirals, where particles circulate in organized paths before ultimately reaching the singularity. These internal currents may mirror, in miniature, the enormous relativistic jets observed outside some black holes, hinting at a connection between hidden internal dynamics and the phenomena we can detect from afar. Magnetic fields inside a black hole are not just passive forces. They are active architects of the interior. They guide particles, shape energy flows, twist light, influence quantum interactions, and organize chaos into structured patterns. Inside the event horizon, these invisible forces create a hidden universe, a realm of motion, energy, and interaction that exists beyond observation, yet profoundly defines the nature of the black hole itself. Inside a black hole, particles collide at velocities approaching the speed of light, creating extreme relativistic effects that are impossible to replicate anywhere else in the universe. Matter falling toward the singularity accelerates relentlessly under immense gravity, and as particles converge, the energy released in these collisions is beyond ordinary comprehension. Electrons, protons, neutrons, and more exotic particles crash into one another, producing cascades of radiation, bursts of energy, and fluctuations in space-time itself. These collisions are not random. They are guided by the intense gravitational pull and the twisting currents of the black hole's interior. In rotating black holes, frame-dragging spirals particles along curved paths, increasing the frequency and intensity of collisions. Streams of matter intersect at high velocities, creating zones of extreme turbulence. Each interaction redistributes energy, heat surrounding matter, and influences the flow of particles further inward, creating a dynamic environment of chaotic motion. The energy amplification from these collisions is staggering. Kinetic energy converts into heat, radiation, and even particle creation, forming a self-perpetuating system of energy transformation. Localized hotspots may develop, regions where matter and radiation swirl violently, colliding repeatedly in a dense, turbulent soup. These collisions create conditions that defy classical physics, blending relativistic mechanics with quantum effects in a dance of unimaginable complexity. Quantum fluctuations further complicate these interactions. Virtual particles pop into and out of existence, interacting with infalling matter and accelerating the chaos. The intense gravitational field stretches and compresses particle wave functions, creating interference patterns, energy bursts, and collisions at scales that are both microscopic and cosmically significant. Inside, every particle is part of a vast network of interactions, a high-energy ecosystem where chaos and order coexist. The resulting turbulence shapes the interior environment profoundly. Energy currents form, vortices twist, and localized flows channel matter and radiation toward the singularity. Collisions produce jets of energy, swirling photon streams and shockwaves that propagate through the interior. Even though this environment is entirely hidden from the outside universe, it governs the fate of every particle falling inward, determining how matter, light, and energy evolve before they disappear into the singularity. Extreme compression during collisions creates exotic states of matter, quark-gluon plasma, hyperdense atomic nuclei, and potentially unknown forms of matter emerge as particles are crushed under tremendous forces. These states contribute to the overall energy dynamics, interacting with surrounding particles and radiation, feeding turbulence, and amplifying the complexity of the black hole's interior. Every collision is both a destructive and transformative event, reshaping matter in ways that challenge our understanding of physics. Relativistic effects amplify the visual and energetic chaos inside. From a theoretical perspective, particles traveling near light speed experience time differently, and their interactions are magnified by both gravity and velocity. Collisions produce shockwaves in space-time, bending paths of other particles and photons, creating feedback loops of energy and motion. The interior is a turbulent symphony where gravity, motion, and energy interact at the extremes of possibility. Magnetic fields and rotation further structure these collisions. Charged particles follow spiraling paths along magnetic lines, while rotation induces frame dragging that curves trajectories. Collisions are concentrated in vortices, streams, and loops, producing zones of repeated high-energy interactions. The interior becomes a dynamic labyrinth of matter, energy, and force, where every particle is guided by both chaos and structure, producing an evolving, turbulent ecosystem. Photon interactions with relativistic particles add another layer of complexity. Light colliding with high-speed particles transfers energy, induces scattering, and creates bursts of radiation that ripple through the interior. Even trapped photons participate in the energetic chaos, contributing to turbulence, heating, and the redistribution of energy. Every particle and photon is part of an interconnected network, a system where motion, energy, and gravity are inseparably intertwined. The interior of a black hole is defined by these extreme particle collisions. Matter accelerates, collides, transforms, and interacts in ways that defy conventional understanding. Energy flows, photons spiral, and quantum fluctuations amplify the chaos, producing a hidden universe of relentless motion. Inside the black hole, collisions are not just interactions. They are the engines driving the dynamics, structure, and mystery of one of the most extreme environments in existence. Inside a black hole, energy moves in relentless, unpredictable ways. Matter falling toward the singularity collides with other infalling matter, radiation, and quantum fluctuations, generating turbulence on an unimaginable scale. Currents of energy twist, spiral, and loop, forming chaotic patterns that constantly evolve. Shockwaves propagate through the interior, rippling across streams of matter and photons, interacting with the black hole's intense gravitational and magnetic fields. Every particle is caught in this turbulent dance, its motion influenced by both local collisions and the global gravitational pull of the singularity. The turbulence inside a black hole is multidimensional. Energy flows not just radially toward the center, but also tangentially, swirling in spirals and vortices. Rotating black holes amplify this motion through frame dragging, causing particles and photons to follow complex helical paths. Streams of matter collide repeatedly, transferring energy and momentum, while photons caught in these flows scatter and interact with particles, producing localized bursts of radiation. This creates a dense, tangled web of energetic motion, a hidden storm that cannot be observed from outside the event horizon. Shockwaves from colliding matter are amplified by the extreme curvature of spacetime. Gravity stretches and compresses these waves, increasing their intensity and creating pressure gradients that accelerate nearby particles. The black hole interior is filled with these propagating disturbances, each one influencing the motion of surrounding matter and contributing to the overall chaotic environment. Particles can experience multiple shockwaves in rapid succession, creating complex interactions that shape the energy distribution throughout the interior. Quantum fluctuations further feed turbulence. Virtual particles pop into existence and vanish, transferring energy to nearby matter, interacting with photons and altering particle trajectories. These interactions are magnified by the intense gravitational field, producing additional localized shockwaves and contributing to the dynamic currents that circulate inside. The interior becomes a turbulent sea of matter, radiation, and quantum energy, with each fluctuation interacting with countless others in a continuous feedback loop. Magnetic fields guide and twist turbulent currents, creating structure within the chaos. Charged particles follow spiraling paths along magnetic field lines, while energy from collisions propagates along these invisible threads. Magnetic reconnection events release bursts of energy, amplifying turbulence and redistributing energy across the interior. The black hole becomes a highly dynamic environment where energy, matter, and force are inseparably connected, constantly reshaping one another. Relativistic effects amplify turbulence. Particles traveling near the speed of light experience time and space differently, and their collisions generate shockwaves with extraordinary intensity. These disturbances propagate through surrounding matter and photons, interacting with magnetic fields and gravitational gradients, creating highly energetic currents that flow throughout the interior. The result is a complex, ever-changing pattern of motion, a storm of energy shaped by both fundamental forces and chaotic interactions. Energy turbulence interacts with exotic states of matter, quark-gluon plasma, neutron-rich cores, and potential unknown forms of matter experience intense acceleration, collisions, and radiation exchanges. These states amplify turbulence, generate secondary shockwaves, and redistribute energy across the interior. Every particle contributes to the dynamic energy ecosystem, participating in interactions that continually reshape the flow of matter, light, and radiation. Photon streams trapped inside contribute to the chaotic environment. Colliding with matter and other photons, they transfer energy, alter particle trajectories, and create bursts of radiation. The interplay between light, matter, and energy forms intricate patterns, like invisible eddies and currents moving through the turbulent interior. Energy is never static. It twists, loops, and spirals endlessly as particles, photons, and quantum effects interact. Temperature variations are extreme. Some regions heat intensely from collisions and compression, while others are relatively cooler, influenced by particle distribution, radiation flow, and quantum fluctuations. These gradients drive further currents, accelerating particles, twisting energy flows, and feeding turbulence. The black hole interior is a multidimensional storm, where pressure, temperature, energy, and motion interact in ways completely alien to the observable universe. The interior is a continuous feedback loop of motion, collisions, and energy redistribution. Streams of matter collide, photons scatter, shockwaves propagate, and quantum fluctuations interact with gravitational and magnetic fields. Each disturbance influences the next, creating a dynamic, constantly evolving environment where chaos and extreme physics govern every aspect of the hidden universe inside the black hole. Inside a black hole, tidal forces stretch and compress matter in ways that defy human intuition. As an object approaches the singularity, the difference in gravitational pull between its near and far ends becomes extreme. This differential force elongates the object into a thin, stretched form, a process scientists have vividly nicknamed spaghettification. Imagine a spaceship or a particle being pulled apart lengthwise, stretched into strands, while at the same time compressed from side to side, creating a warped, twisted form that seems to defy normal dimensions. The physics behind spaghettification is grounded in general relativity. Gravity near the singularity is not uniform. It increases dramatically over very small distances. The closer an object gets, the stronger the pull on the nearest part, compared to the farthest part. In this environment, even atoms and subatomic particles are subject to immense tidal forces. Molecules stretch, atomic bonds deform, and the very structure of matter is pulled toward the singularity in an intense, relentless motion. Rotation complicates spaghettification further. In rotating black holes, frame dragging twists and spirals matter as it is stretched, producing helical elongations. A falling object may not only be pulled lengthwise, but also rotated, spun, and twisted as it descends. The combination of stretching, compressing, and twisting creates a dynamic distortion unlike anything observed elsewhere in the universe. Matter does not fall smoothly, but is caught in complex spirals and vortices shaped by gravity and angular momentum. The internal currents of energy in photon streams interact with spaghettified matter, adding turbulence to the stretching process. Particles collide, scatter, and exchange energy continuously while being elongated, creating a chaotic, energetic environment. Each particle is both stretched and accelerated, participating in collisions that further redistribute energy and momentum throughout the interior. Matter and energy are inseparably entwined in this extreme environment. Quantum effects influence spaghettification as well. Virtual particles, quantum fluctuations, and exotic states of matter experience the stretching forces differently, creating localized distortions and fluctuations within the larger stretching pattern. These effects amplify the extreme environment, producing bursts of energy and complex motion that ripple through nearby matter and radiation streams. The interior becomes a turbulent weave of stretched, spinning, and accelerating particles. Spaghettification also affects light. Photons passing near stretched matter are bent along extreme curves, scattering in unexpected directions, producing interference patterns that influence the motion of other particles. Energy is continuously redistributed through these interactions, and the paths of light, matter, and radiation intertwine in a tangled, chaotic web. The interior of the black hole becomes a multidimensional system, where every strand of stretched matter interacts with surrounding energy flows. Different regions inside the black hole experience varying degrees of spaghettification. Near the event horizon, tidal forces may stretch smaller objects modestly, while larger structures undergo extreme elongation closer to the singularity. The interior is layered with zones of distortion, each with its own energy currents, particle interactions, and photon dynamics. Matter is constantly pulled, twisted, and stretched along multiple axes, producing an environment in continuous flux. High-energy collisions amplify the effects of spaghettification. In falling, matter accelerated to near-light speed interacts violently with other streams, causing sudden bursts of stretching, compressing, and twisting. These collisions create localized shockwaves that propagate through nearby matter, producing dynamic distortions and turbulent energy flows. The interior is a storm of spaghettified particles and radiation, where chaos and structure coexist in constant motion. Temperature extremes interact with tidal forces to further influence spaghettification. Hotter regions of matter expand and accelerate differently from cooler areas, producing differential stretching and compression. Pressure gradients, energy flows, and magnetic fields combine with tidal forces to create a multi-dimensional, high-energy environment. Matter is never static. It stretches, twists, collides, and accelerates in an unending cycle of extreme physics. The phenomenon of spaghettification is central to the internal dynamics of a black hole. Matter, energy, photons, and quantum fluctuations are all subject to these extreme stretching and twisting forces. Tidal forces guide the motion of particles, shape energy currents, and influence interactions in ways that are both violent and precise. The black hole interior becomes a realm where space, matter, and energy are continuously contorted, creating a hidden universe governed by forces far beyond ordinary experience. At the very heart of a black hole lies the singularity, a point where our understanding of physics is pushed to its absolute limits. Gravity becomes infinitely strong, curving space-time beyond recognition, and matter and energy are compressed into a state unlike anything else in the universe. The singularity is not a surface or a solid object, but a region where all the matter that has fallen inward accumulates, squeezed into an incomprehensibly dense core. Particles, radiation, and energy streams converge, interacting in ways that are completely alien to the physics experienced outside. Matter falling toward the singularity experiences extreme acceleration and compression. Every particle is stretched, twisted, and collided with countless others. As atomic and subatomic structures break down under the immense tidal forces, matter transforms into exotic states, possibly quark gluon plasma, or forms not yet understood by modern physics. Energy flows from these interactions, feeding turbulence and reinforcing the chaotic, dynamic environment surrounding the singularity. The singularity is also a theater for extreme space-time distortion. Time itself behaves differently, with clocks theoretically stopping relative to distant observers. Space is no longer a continuous, flat stage, but a curved, warped landscape where conventional directions lose meaning. Particles, photons, and energy streams follow paths dictated entirely by this warped geometry, moving along trajectories that bend and twist unpredictably. Quantum fluctuations near the singularity are magnified dramatically. Virtual particles, fields, and exotic quantum states interact with the compressed matter and extreme energy currents, producing localized bursts, collisions, and energy redistribution. These interactions may contribute to phenomena like Hawking radiation in the external universe, hinting that the singularity's extreme interior may subtly affect the observable world, despite being hidden behind the event horizon. In rotating black holes, the singularity may form a ring-like structure, creating unique internal dynamics. Matter and energy spiral around the ring, experiencing rotational forces in addition to gravitational compression. This rotation produces vortices, chaotic flows, and complex paths for particles and photons. The interior becomes a multidimensional environment where centrifugal and gravitational forces interact to shape the convergence of matter and energy at the core. Light entering the singularity does not simply vanish. Photons are bent, stretched, and trapped along complex trajectories, interacting with other particles and energy currents. The singularity acts as a focal point for all energy streams within the black hole, concentrating motion, radiation, and matter into the ultimate high-density environment. Even waves of gravity generated by falling matter interact with this core, producing ripples of space-time that influence internal dynamics. Temperature and pressure reach extreme levels. The core is unimaginably hot and dense, with particles squeezed together at scales beyond comprehension. Matter cannot maintain ordinary atomic structures, and energy densities exceed those found in the cores of stars by orders of magnitude. This environment is a crucible where matter and energy are inseparably fused, creating conditions that challenge every law of classical physics. Interactions near the singularity also involve feedback with the surrounding interior. Collisions, magnetic fields, photon streams, and energy turbulence all converge at the core, influencing particle trajectories and energy distribution. Streams of matter spiraling inward may collide, merge, and redistribute energy, creating dynamic currents that pulse outward into the surrounding interior, feeding the chaotic ecosystem of the black hole. The singularity is a boundary of knowledge. Physics breaks down here, and general relativity meets quantum mechanics in ways that remain mysterious. Space and time are compressed, matter is transformed, and energy circulates in ways that defy intuitive understanding. The interior of the black hole becomes a laboratory of extreme conditions, where the convergence of matter and energy produces an environment entirely disconnected from conventional reality. Every particle, photon, and quantum fluctuation that reaches the singularity becomes part of a dense, energetic convergence. Motion, energy, and matter fuse in an intricate, high-density network, governed by the extreme forces at the core. The singularity is the ultimate endpoint of the black hole interior, a region where the known laws of physics are stretched to their limits, and the mysteries of the universe concentrate in a single, hidden point. Thanks so much for watching. Tonight, we explored mysteries beyond time and space. And if your mind is still buzzing, that's exactly where it should be. If you're curious for more, check out our other videos filled with history, science, and the unknown. Drop a comment to share your thoughts or tell us where you're watching from. Keep wondering, keep imagining, and let every story take you further than you ever thought possible.